Hello and welcome to today's webinar. We want to talk about lithium-ion battery testing, especially about performance, health, and lifespan tests. I am Dr. Frank Richter. Originally, I come from nanotechnology, but I got my PhD in chemistry at NTNU in beautiful Trondheim, Norway. I will be talking at one more conference this year. You see a yellow highlighting. I'm gonna talk at the Battery Experts Forum in Darmstadt, and I give a workshop on battery aging. It takes place from the 7th to the 9th of November. So if you're in Darmstadt, come by and we can have a chat. I have a history in maritime and in automotive battery development, maritime with Siemens in Norway and automotive battery development with ACA, mainly with Volkswagen in Germany. You can find some of my publications, for example, in Electrochemica Acta or in the Journal of Power Sources. Today I talk to you as the CEO of Greenectra, which is a coaching and consulting company within the lithium-ion development industry. So today we have three topics: capacity testing, DCIR testing, that's direct current internal resistance testing, sometimes we call it pulse testing, and we also talk about aging testing in real life, and we will see in a second what that means. Let's get started with capacity testing. It's basically answering the question how many amp hours you have in your battery. Let me repeat, it's not about watt hours, it's about amp hours. And it's also a typical test as a part of aging testing, because batteries lose capacity as they age. It's not really rocket science, especially at room temperature. We basically fully charge the battery, and during discharge, we do Coulomb counting, which is a fancy way of saying we measure time and current. If you discharge a battery at 10 amps for 1 hour, that is 10 amp hours, right? And amp hour is already the correct unit of capacity, so it's not really that complicated. There's a small challenge at temperatures other than room temperature, but we should start with room temperature first. What we want to do first is to CV charge our battery to 100% SOC, that's state of charge. CV, that means it's a two-step charging process with a CC step, that's constant current, and a CV step, that's constant voltage. And we typically have some sort of equilibration period, and 2 hours is quite a reasonable value. It could be sometimes a little less than 2 hours, sometimes maybe even a little more. It really depends, but 2 hours is a good number. Once the battery is fully charged, we want to discharge, but we do this discharge at a very, very low rate. For example, C over 30 or even C over 40, which means the whole discharge from 100% state of charge to 0% state of charge is going to take us 30 or even 40 hours. After discharging, we also charge the battery at this very low rate to the upper voltage limit. And as mentioned before, we do Coulomb counting during the whole measurement. We measure our current and we stop the time. Let's have a look at a capacity test at a temperature other than room temperature. In that case, we add two recalibration steps, one after the discharge step and one after the charge step. This recalibration is done at room temperature, and there is another equilibration period. During recalibration, the cell is then charged or discharged to the lower voltage limit after the discharge step and the upper voltage limit after the charge step. You may ask, why do we need to get the battery to the lower voltage limit after we just got the battery to the lower voltage limit? Well, discharging to the lower voltage limit is not the same thing at all temperatures, and it will become clear when we will be looking at an example on the next slide. This recalibration is done to get information about the difference in discharge capacity and the difference in charge capacity, both comparing the actual test temperature and room temperature. The recalibration also serves as data for state of charge calibration at temperatures other than room temperature. I think it's the easiest just to look at an example. Let's do an example, a capacity test at 0 degrees Celsius. First, we want to do a CV charging to 100% state of charge at room temperature. That's right. Even though we want to measure the discharge capacity at 0 degrees Celsius, we charge it at room temperature. This gives us a very well-defined and comparable starting point for all capacity tests. After charging the battery at room temperature, we change the temperature to the actual test temperature, in our case, 0 degrees Celsius. Typically, your battery would be in a climate chamber, and you would basically just switch the temperature to 0 degrees Celsius. But of course, after just switching to 0 degrees Celsius, the whole battery does not have a temperature of 0 degrees Celsius like immediately, but we want the whole battery to be at 0 degrees Celsius. That's why we need to wait. And the typical waiting time, or you could call it a typical thermal equilibration time, that's again something around 2 hours. Now, we do the discharge at the test temperature at 0 degrees Celsius, and we discharge to the lower voltage limit. You can see in this example, I chose a rate of C/30, which means this discharge takes us 30 hours. And now it's time for recalibration. Once again, we change the temperature to room temperature and we wait for 2 hours, so the whole battery cell is at room temperature. And during this temperature change step, our voltage will also change a little. And after the thermal equilibration for at least 2 hours, we discharge or charge the battery to the minimum voltage. So basically we discharge if our voltage is slightly above the minimum voltage, or we charge if our voltage is slightly below the minimum voltage. And in this recalibration step, we basically measure the difference between a discharge at room temperature and a discharge at the test temperature, or at 0 degrees Celsius in our case. After this recalibration, we change the temperature to the test temperature, 0 degrees Celsius. And we wait for the thermal equilibration. Now, we charge the battery to the upper voltage limit. Once again, at a very low rate, you see C/30, so this charging process will also take us 30 hours. And now it's time for the second recalibration step. We change the temperature to room temperature, and of course we wait for thermal equilibration, so we wait for another 2 hours, and now we charge or discharge the battery to the maximum voltage at this low rate. And of course, we do Coulomb counting during the whole measurement. If you look at these steps, look at the black steps. This is basically the capacity test at room temperature. Look at the blue steps. These are the steps which you need for temperature changes and the thermal equilibration at the new temperature. And the red steps, these are the recalibration steps at room temperature. I want to make some final remarks on the capacity testing. First of all, why do we discharge at such a super low current rate like C/30 or C/40? Why does this whole measurement take that much time? Why does it need to take that much time? Well, measuring at a very low rate means being very close to the actual capacity. Because, and this is important, capacity is not a function of the discharge rate. Okay? Capacity is a theoretical value, the theoretically available discharge capacity at an infinitely small current rate. Of course, there can be very practical measurements, right? Like practical discharge capacity at certain higher rates, like C over 2 or 1C or 2C, whatever, right? You can ask the question, how many amp hours do I get when discharging the battery at this or that current? But in that case, you measure a practical discharge capacity. You do not measure discharge capacity. Okay? And practical available discharge capacity is of course a function of discharge rate, a function of temperature, you name it. Why? Well, when you discharge, you get a voltage drop due to the internal resistance of the battery. And this voltage drop follows Ohm's law, as you can see. You will get a large voltage drop at high internal resistances, which is the case at low temperatures. And you get a large voltage drop at high currents. And the larger the voltage drop, the earlier you reach the minimum voltage limit during the discharge. And that's also the reason why when measuring actual capacity, we use super low current rates. If the current is very, very low, the voltage drop due to the internal resistance is also very, very low, and we can discharge and measure the full capacity. Our next test is the DCIR test. Let me remind you, DCIR, that is direct current internal resistance. Sometimes we call it pulse testing, and you can see a test with 2 pulses on the right side. The important part here is the discharge or the charge pulse. We see a discharge pulse, 20 amps. You can see the voltage goes down, and we see a charge pulse, it's minus 20 amps, and you see the voltage is going up. First of all, let's have a look at the graph on the right side, right? We see in the very beginning, basically nothing is happening. The voltage is constant and the current is 0. So nothing happening, right? After 20 seconds, there is a discharge pulse of 20 amps for 18 seconds. And later on, we have a charge pulse of minus 20 amps for, I think it's 10 seconds. Yes. Now, we have a look at the calculation. Okay, we calculate the DCIR for 18 seconds using Ohm's law. The DCIR for 18 seconds, that is the total voltage drop during this 18 seconds. This is something you can measure, right? And we divide it by the current. The current we also know. It's 20 amps. We use Ohm's law, okay? But the DCIR is not the ohmic resistance. The ohmic resistance can also be calculated. You also calculate it using Ohm's law, but you use only the immediate voltage drop once the current is turned on. You see, the voltage is jumping, and this jump, well, responsible for this jump is the ohmic resistance of the battery cell. So when you want to calculate the ohmic resistance, you want this voltage jump or voltage drop, the immediate voltage drop. But when you want to calculate the DCIR for 18 seconds, you need this whole voltage decrease during the whole 18 seconds. So why do we do DCIR testing? Well, it tells us how much the voltage drops due to internal battery processes. Important for the application is the power, right? Power, that is voltage times the current. But for your application, it's important what voltage you have on the terminals or on the taps of the battery, right? So, but this voltage is already reduced due to internal battery processes. DCIR testing is also useful for some basic heat generation models, and it's also very important data for the battery management system, for example, for the calculation of available discharge power. Now, here comes the challenge. DCIR testing can be carried out at different states of charge. It can be carried out using different pulse durations, right? In our example, we used 18 seconds, but it could be like 1 second, 0.1 second, could be 30 seconds, right? It can be carried out at different current rates. In our example, we used 20 amps. It can be carried out at different temperatures. It can be carried out at different states of health, meaning it can be done for a new battery, for a slightly aged battery, for a battery that aged a lot, right? It can be carried out in the charge and the discharge direction. So a full DCIR characterization of a battery cell takes a lot of time. So basically, it's not really feasible to do a full DCIR characterization. What you typically do is you find some combinations of SOC, pulse duration, current rate, temperature, SOH, and charge or discharge direction. You find some combinations of these values and you set up like a limited test matrix. Please allow me to make some final remarks on the DCIR testing. And I want to talk about high currents and long pulse durations. Why is that important? Well, the DCIR is a function of the state of charge. That means the DCIR for 18 seconds does not necessarily have to be the same for like 100% state of charge and 20% state of charge, right? That can be different. Okay, now, the longer the discharge time and the higher the current, the higher is also the delta state of charge. Which delta am I talking about? Well, let's have a look at our discharge pulse again. We had a discharge pulse, it was 20 amps, and we started the discharge at this point and it ended at this point. But a discharge pulse, right? So this is a discharge, which means we have a slightly higher state of charge here and a slightly lower state of charge here. Now let me just make up some numbers. This could be at like, let's say 41% state of charge, and this could be at 40% state of charge. Now, DCIR is a function of state of charge. So which DCIR did I just measure here? Was it the DCIR at 41%? Or was it the DCIR at 40% state of charge, right? I can see a problem, and I think you see it too. There is a difference in the state of charge, so there is a challenge in the definition of the DCIR at certain state of charge values, because you always start the pulse at a certain value and you end the pulse at a certain state of charge value. So I would say always very carefully look at the test description and the DCIR definition. So the last testing for today, that's aging testing. And during aging, the battery loses capacity and the internal resistance increases. So what do we want to measure, right? We want to measure capacity and we want to measure internal resistance, for example, the direct current internal resistance. And the capacity and the DCIR tests are really the most typical aging tests. But there is also other tests carried out at different states of health, which means at different capacities compared to a new battery. For example, the open circuit voltage changes as the battery ages, or more precisely, the relation between the open circuit voltage and state of charge. Okay, so self-discharge changes as the battery ages. The practical discharge capacity also changes, not only discharge capacity, as the battery ages. Some safety tests are carried out at different states of health, and you typically define two special state of health points, so to say. You have special importance at the end of warranty, EOW, and the end of life, EOL. So the definition of what is end of warranty and what is end of life, this could be different for different projects or different OEMs, right? A typical value could be the end of warranty at, let's say, 75% state of health, for example, and the end of life could be at 50 or 55% state of health. Okay. We want to do aging testing. So we have to ask ourselves the question, how do we age the battery, right? How do we make the battery lose capacity? And there are two ways: calendric aging and cyclic aging. Calendric aging, that's basically putting the battery on a shelf at a certain temperature and waiting. And cyclic aging, this is really the operation of the battery, right? Like charging, discharging, charging, discharging. And depending on the application, different aging tests need to be carried out. And I want to have a look with you at some practical examples. What you can see here is a test matrix for a calendric aging experiments. You can see the test is carried out at different states of charge and at different temperatures. And for each of these test conditions, for example, 45 degrees Celsius and 100% state of charge, you have 5 batteries. But you don't write batteries. I use the term DUT, device under test, because in 99% of the test descriptions you will find the term DUT. The important point here is that you have to ask yourself the question, every how many days shall we perform a capacity and a DCIR check, right? As the battery ages, for example, at 45 degrees Celsius, at 100% state of charge, the battery loses capacity, and you want to measure this losing of the capacity. But the aging testing influences the aging. What do I mean? Well, calendric aging, that is really just putting the battery on the shelf and waiting, right? But aging test, well, to test the aging, you need to discharge the battery because you need to measure the capacity, right? But if you measure the capacity and you discharge the battery and charge it up again, well, in that case, the battery is not just waiting on the shelf, right? So this influences the aging behavior. So obviously you don't want to measure like every day, but you also don't want to measure like once a year, because during this 1 year of being on the shelf, you lose a lot of capacity, and you, so to say, you want to say something more than just, okay, during this 1 year, my battery lost 10% capacity or whatever, right? So a typical value could be like every month or every second month. You could, so to say, do a capacity check and a DCIR check. And if you are at higher temperatures, for example, like 45 degrees, you lose capacity a little faster. You could consider maybe doing the capacity test every second week, but every second week, that is already quite often, I would say. The second example, that's the cycling aging matrix. And we can do cyclic aging at different state of charge windows, right? You can cycle the battery between 0% and 100% state of charge, which means between a totally empty and a totally full state. But you could also restrict the state of charge in a way that you say, hey, I don't charge up to 100%, I go only to 80% state of charge, and I also don't fully discharge the battery, I only discharge down to 20%. Okay, and basically you can find a matrix with different state of charge windows and different temperatures again. And now, very importantly, this you can also do at different current rates, right? It's cyclic aging, which means we need to cycle, which means we need to discharge, and discharge is done at the current, and this current rate could differ, right? So for cyclic aging, it's not only the temperature and the state of charge window defined, it's also the current that needs to be defined. And once again, you have to ask yourself the same question like with the calendric aging experiment. Every how many cycles shall we perform a capacity and a DCIR check, right? So what is a typical value? Sometimes you find every 100 cycles, every 200 cycles, right? You do a capacity check. So why is this now once again influencing the aging itself? You could ask yourself the question, hey, when I cycle the battery and I charge the battery and I discharge, I can just measure capacity, right? Well, yes and no. if you discharge the battery at a very, very, very low rate, for example, C over 30 or C over 40, then this data will give you the capacity of the battery. But if you have more practical experiments, like 1C, 2C, 4C, right, at higher current rates, well, in that case, you're not really measuring capacity. You're measuring practical capacity. But what you want to measure is capacity. Okay? So, once again, you measure some sort of practical capacity during the cyclic aging, but that's not really what you want. You want to measure capacity, and this is done at a really, really low rate. And of course, a cycle at a low rate is something different than a cycle at a higher rate. So once again, the testing of the capacity influences the whole aging behavior. And I mean, if you do the capacity check at a rate like C over 30 or C over 40, that's 40 hours of discharge, that's 40 hours of charge. It takes a lot of time. Just for that reason, you don't want to do it every day, obviously. So let's say every 100 cycles, every 200 cycles. That's a reasonable value in most of the cases. Now, we are back at the same question. How shall we age the battery? Shall we do it at a constant current? Shall we do it at a constant power? This is not really realistic, right? For a car, it does not have a constant power. It does especially not have a constant current during operation. So what is a realistic driving profile? That's a good question. And average driving profile, that was already defined in the past. It's the WLTP, the World Harmonized Light Duty Vehicles Test Procedure. In the past, you used this to measure typical exhaust values of a car. But now we use it to calculate the power profile on a single battery within the whole battery pack. Okay, so the WLTP takes into account that standard testing, like in the battery lab, what is very typical at constant currents or constant power, that's not really real operation. So in a real life scenario, and that is something that we wanted to talk today about, in a real life scenario, you have a varying power profile. And this needs to be defined, and it is defined with the WLTP. So, as I mentioned, based on this WLTP profile, you need to answer the question, what does this profile, this standard operation, mean in terms of the load to a single battery in your battery pack? Because you want to run the test on the single battery level. Well, this power profile for the single battery cell depends on, well, of course, on the definition of the WLTP cycle itself. If this definition changes, the power profile for the single battery also changes. But more importantly, it also changes for different battery systems, right? How many battery cells do I have in the modules? How are they configured, right? How many do I have in series? How many of these in series strings do I have in parallel? This all influences, so to say, the power profile on one single battery within the whole pack. And the current rate on cell level also depends on the battery chemistry. So it's different for an NMC, nickel manganese cobalt oxide battery, and for a LFP, like lithium iron phosphate. And it's also a function of the capacity of the battery. Okay, so it varies, but it's also not that difficult to calculate the power profile for your single battery. What I want to highlight here is that the WLTP cycle aging, once again, it's cycling with a varying power, right? It's not a constant C rate like in the lab. And how often do we do these checks? Well, once again, capacity and DCIR checks can be done every 100 or 200 cycles, maybe every 50 cycles if you do it at a slightly higher temperature. Finally, I want to talk about two typical questions or two typical tricks of battery manufacturers, which I have seen in data sheets, and I'm not blaming any manufacturer. I just say I saw it. Okay? First question or first trick. What's the C rate of an aged battery? Why is that an important question? Well, C rates are standardized rates. And the 1C rate, for example, is the current at which you can fully discharge or fully charge the battery within 1 hour. Let's take an easy example. A battery with a capacity of 50 amp hours, you can discharge within 1 hour utilizing 50 amps of current. 50 amps times 1 hour, that's 50 amp hours, right? Not really rocket science. And this 1 hour discharge current, that's the 1C rate. But the important point is that this is always defined for a new battery, a pristine one, which means a battery of a state of health of 100%. So where's the problem? Well, let's assume our 50 amp hour battery aged and it lost capacity, and we have only, let's say, 40 amp hours capacity left. So this 40 amp hour capacity you can fully discharge within 1 hour utilizing 40 amps, not 50, right? But the C rate is always defined for the new battery. That means even for the aged battery with 40 amp hours capacity only, the 1C rate is still 50 amps, not 40 amps, because C rates don't care about state of health. C rates care about the capacity for the new battery. So, and if you actually decrease the C rate as the battery ages, if you wrongly do that, you utilize smaller currents. And using smaller currents means slower aging, which means the battery looks better than it actually should. So really double check that when looking at aging graphs in battery data sheets. The second question, or the second trick, what is one full cycle? Well, one full cycle, that refers to the discharge capacity plus the charge capacity of a battery, once again at 100% state of health, a new battery. Okay, and let's take our example again. A battery, it's new, it has 50 amp hours, and we have a discharge capacity of 50 amp hours and a charge capacity of 50 amp hours. So during one cycle, we have a capacity throughput, we could say, of 50 amp hours plus 50 amp hours, that's 100 amp hours. And I guess you see it. If the battery is aged, let's say we have only 40 amp hours discharge capacity left, in that case, one full discharge plus one full charge, that is 80 amp hours capacity throughput. And yes, this is one full discharge and one full charge, but it's an aged battery, so that's not a full cycle. And this is why it is more elegant to look at the capacity loss as a function of capacity throughput of a battery rather than the capacity loss as a function of cycles, because the cycle definition may be wrong and it can be quite difficult to spot. That's why when you see a battery data sheet and it mentions capacity loss as a function of cycles, look for the definition of the cycle, and if you don't find it, ask for it. Last but not least, I want to make you aware of our next BAT-Excel International. It's a comprehensive 6-week program on operation, testing and safety of lithium-ion batteries. It's a hybrid online course, which means we have online self-study modules with online videos, quizzes, and other interactive material, as well as live coaching sessions. And we have Q&A live coaching sessions. We limit the number of participants to 15 because I want everyone to be able to ask their own individual questions within these live coaching sessions. And you don't only learn from me, you learn from the best. You learn from international leading experts. If you want to check them out, check greenectra.com/our partners. And last but not least, there is a discount code. If we are not already sold out, And if it's not already the 28th of October, you can apply the discount code webinar minus testing minus 20% minus off. And you can guess it, you get 20% off using this discount code. That's it for today. I hope I see you in the next Bad Excel International, and I wish you a great day. Bye bye.